yesterday, to construct the character table of A4. So A4 are the even permutations on a set of 4 elements. Cardinality of A4 is 12. Cardinality of the set of conjugacy classes in A4 is 4. So we have 4 irreducible, non-isomorphic representations of A4. So 4 irreducible, non-isomorphic representations of A4. So now here I will construct the character table. So we do this. Let me see. So we have identity. Then we have the 2 cycles. And remember, there are 3 of them. Then we have the 3 cycles. And there are 4 of them. And we have the other set of 3 cycles. You remember, the 3 cycles in A4 fall into 2 conjugacy classes. And so we have the other cycles are AI, KJ, and 4 of them here. So we always have the trivial representation. And the character table, it's easy, 1, 1, 1, 1. 1, 1, 1, 1. Then we have another representation which we can guess, and it is the restriction of the representation of the permutation of basis element of C4. And then you remember this preserves this space V0, where is the hyperplane where sum of coordinates is 0. So then we have rho 2. Rho 2 is, so let's say, let's write here characters of A1. Rho 1 is trivial. And rho 2 is permutation representation. And now we compute the characters of chi2. So rho 2 is the restriction to A4 of the permutation representation of S4. So the one that permutes the basis element and preserves preserves the decomposition of C4 equal to V0 direct sum Okay, so S4 acts on C4, preserve this space. This is Z1 plus Z2 plus Z3 plus Z4 is equal to 0, and this is, we call it W. So S4 acts here as identity, and so does A4. Likewise. And A4, of course, also preserves this subspace, because S4 does. And now we are going to compute the characters. Okay, now the characters of the identity will be 3, because this space is 3-dimensional. Huh? So here we get a 3. And then on 1-1 cycles, the character is -1. Why? Because, remember, if I take, for instance, no, I erase something here. if I look at the permutation representation, let's say rho 2 of the cycle 1, 2, you remember is given by the matrix 0, 1, 0, 0, 1, 0, 0, 0, 0, 0, 1, 0, 0, 0, 0, 1. So this is the matrix of the action on all of C4. And so the trace of this matrix is 2. But remember, this matrix acts trivially here, so we always have to remove the contribution of this subspace. So the character, and then if we have a 2-2 cycle, we have to multiply 2 of these matrices. For instance, if I get 1, 2, and then I look at 1, 2 of 3, 4, I get 1, 0, 0, 0, 0, 1, 0, 0, 0, 0, 0, 1, 0, 0, 1, 0. If I want to know how rho 2 acts on the 2-2 cycles, I have to multiply these two matrices. So it's a homomorphism. So what I get is, for instance, that rho 2 of 1, 2, 3, 4, which is sufficient for us to know this to compute the character, no? Because the character is constant on conjugacy classes. The matrix that we get is 0, 1, 1, 0, 0, 0, 0, 0, and then 0, 0, 0, 0, 0, 1, 1, 0. Okay, now the character of this matrix is, the trace of this matrix is 0, but we have to subtract 1. So we get minus 1. Here is minus 1, you see. Now we go on the 3 cycles. On the 3 cycles, well, it does what... on 3 cycles, it's enough that we compute the trace, for instance, of rho 2 of 1, 2, 3. The matrix of 1, 2, 3 is 0, 0, 1, 0, 1, 0, 0, 0, 0, 1, 0, 0, 0, 0, 0, 1. The trace is 1, but we have to remove 1, so we get 0. 0, and likewise on the other 3 cycles. Same reasoning. The big matrix has trace 1, no? For instance, I don't know, if I do 1, 3, 2, I get 0, 1, 0, 0, 0, 0, 1, 0, 1, 0, 0, 0, 0, 0, 0, 1. Again, the trace is 1. I have to remove the contribution that comes from W, and I get 0. So I get another 0 here. Okay, so of course now I restricted the representation of S4 on the space V0, but I don't know yet whether it remains irreducible, for instance. But now we use the theorem that says that this representation is irreducible if and only if its characters as norm 1. So let's compute the norm of this chi2. So if I do the norm of chi2, if we compute chi2, maybe I'll get a better marker. This will be 1 over 12. And now I need, so 3 squared plus 3 times minus 1 square plus, all the rest is 0, no? 4 times 0 square plus 4 times 0 square. So what I get is 1 over 12, 9 plus 3, 1. So this guarantees that the representation of rho 2 remains irreducible once I restrict it to V0. Okay, now we have 2 out of 4. We still have to construct 2 more. But then, now let's think that how do we construct them? We have to think this. Okay. Now observe that A4, the commutator of A4 is a group isomorphic to V4. So it's a normal subgroup of A4, and what we have is that A4 over V4 over its commutator is isomorphic to symmetry. So now we think about the representations of Z3, which we constructed yesterday. You remember, there were the powers multiplication by powers of primitive cubic root. You remember? And now what do? We say, okay, I take a representation of A4 that acts as the identity on V4 and is compatible with the ones that it is restricted to Z3, to the Z3 embedded in A4, does exactly what the reducible representations of Z3 do. So we say that rho 3 and rho 4 are obtained by lifting to A4 the two irreducible one-dimensional of Z3. So what do? So rho 3 is okay, this V4 inside A4 are the two cycles, just to make it clear. So this V4, this is formed, it consists of the two cycles, the 1 and the 2 cycles. Clear that they are a normal subgroup because cycle types is preserved by conjugation, right? Okay, so I define the representation rho 3 on the class of 1, 2, 3. We let it's multiplication by z, where z is a primitive cubic root of 1. And rho 4 on 1, 2, 3 will be multiplication by z squared. Okay, I gave the representations on the generator of this quotient. It's enough. So what do I get now? So I get, so we said rho 3 is multiplication by z. Okay. And rho 4 multiplication by z squared. They're both one-dimensional. This is so now we are computing the characters. Okay, so they are one-dimensional. So for chi3 on the identity is 1. Then we have that on the 2 cycles, which are in the kernel of the representation, it's 1, right? So here is 1. Then on 1, 2, 3 is z, and here, no, I made a mistake. Okay. Oh yes, it's z, and on the other one is z squared, because 1, 2, 3, the class of 1, 2, 3 square is ends up in the class of 1, 3, 2. So we get z squared, the square. And below we have again 1 for the character of the identity, 1 for the character of the 2 cycles, 2 cycles, and then we get z squared. And here we would get z4, which is the same as z, because z cubed is 1. So this is the character table of A4. Maybe we should check a few the relations. For example, what do we want to check? We want to check that Rho 3 and Rho 4 are non-equivalent. Well, that we can look at Rho 3 and Rho 4, they differ at least at one element. Maybe we would like to check that their characters are actually orthogonal. Okay, let's make a check. Okay, let's check that is 0. It has to be so because they are non-equivalent. The characters are not identical as functions. No, so you see. Okay, so (1 over 12), and now we have to do the product, 1 times 1, 1, plus, again, 3 times 1 times 1. You see, here we use really the cardinality of each conjugacy class. So 3 times 1. Then we have 4 times z square bar, plus 4 times z square z bar. And now we look, we get 1 over 12 1 over 12. So here what we are, so here we get 4 plus okay, z bar is 1, so we get here 4 times z bar. We are left with z bar plus z. Okay, so now this piece here, it is 2 times the real part of z, real part of z, and where z sits. You see, we took z be a primitive cubic root of 1, so sits in a z sits, for example, in this vertex of the equilateral triangle inscribed in the unit circle. So this xi This is Z, this is Z bar. And then you know that the real part here is minus 1. So this is 2 times minus 1, which gets minus 2. So minus a half, sorry. This is minus a half, and altogether we get minus 1. We get minus 1. So here we get 1 over 12. Did I say 4 minus 4, 0. So you see, this guarantees that the two representations are irreducible, they are dimension 1, but they are non-equivalent. And so, for instance, you could check that each of these rows has norm 1, and so on. Clear? More questions? Okay, now we pass to S4. Okay. So now we construct the character table of S4. Okay. So we have S4. Cardinality of S4 is 24. And then we have the cardinality of the set of conjugacy classes is 5. So 5 irreducible non-isomorphic representations. And now again, we try to construct the character table. So the conjugacy classes are 1, 2 cycles. But let me try to see whether I can use the same order. Yeah. So 2 cycles. These are 6. The cardinality of this conjugacy class is 6. Then we have 3 cycles, I, J, K, class of cardinality 8. Then we have the 4 cycles, I, J, K, L, cardinality 6. And then we have the 2 cycles, I, J, K, L. And these are 3. Okay, so we start with row 1 is equal to the trivial representation, and so the character is 1, 1, 1, 1, 1. Then we have the sign representation. You remember, is the homomorphism from S4 to plus or minus 1 that sends in 1 the even representations, the ones that we saw earlier, A4. So this is the sign. It's a well-defined homomorphism, no, from S4 to plus or minus 1. And the character, so is 1. And then the 2 cycles are odd, so they go in minus 1. The 3 cycles are even, they go to 1. 4 cycles are odd. 2 cycles are even. So here they are. So we have 2 one-dimensional representations with different characters, so these certainly are non-equivalent. Now we go back to the row 3 is the permutation representations, the one that we already discussed early. Row 3 is the permutation representation. So it's 3-dimensional, and we already checked that it has value. The trace is 1 moment. Let me see if I. Yeah. 3 is value 1. The character is 1 on the 2 cycles, 0 on the 3 cycles, minus 1 on the 4 cycles, and -1 on the two cycles. Okay. Again, you can reconstruct all the matrices, just knowing what they do, what rho 3 does on the two cycles, then you can construct all 4x4 matrices for any element of S4. No? Every element of S4 is a product of of two cycles, transposition. You multiply the matrices because it's a homomorphism, and then again, when you compute the trace, you have to remove the contribution of span of 1, 1, 1, 1, where the group acts as the identity, and then you get these values. Another representation that comes right away is the product of R2, the composition of, let's say, of R2 and rho 2 and rho 3. So you have the permutation representations, and then you multiply by -1 all matrices which are coming from odd cycles. So rho 4 is rho 2 times rho 3, and the character of rho 4 is, of course, 3 as the dimension, because the dimension is the same. Then here you get -1 on the transpositions, which are odd. You continue to get 0 on the 3 cycles. You get 1 here and 1 here. No, -1 here. Why -1 here? Pyramid matrix. Okay. Two. -1 here because you have to. How is it? I forgot. -1. I took the matrix. -1, 1, 2, 3. -1, what? Yeah, certo, right, of course. Sorry. 2, 3. Yeah, it is a product, yes, sorry. Okay. So now we are left with the fifth representation. The fifth representation. Oh, I thought I wrote the matrices, but okay. Now, to construct the fifth representation, again, we have to make an observation. So, rho 5. Okay. So we have to observe one thing, is that if we take a V4, so it means the two cycles, these form a normal subgroup of S4. So this for a normal subgroup of S4. So these are the two cycles. So we can take the quotient, and the quotient S4 over V4 is isomorphic to S3. So again, we can do the same trick as we did earlier to construct some of the representations of A4. Okay, so I take a representation of S3 and I lift it to S4, imposing that is the identity on V4. Well, a natural representations of S3 we did them yesterday. So they are the trivial one, the sign, and then we have a two-dimensional one, which is non-trivial, right? So we construct now row 5 as follows. So we have S4, then we have the projection to S3, and then here we take the permutation representations of S3. So R of S3, two-dimensional, the irreducible one, two-dimensional one. Where V0 this time is sum of coordinates is equal to 0 in C3. Okay, so we compute the character just using the character table of S3. And so we have, so here row 5, chi 5, so dimension 2. Then what do we have? So the 2 cycles, on the 2 cycles we have 0. On the 3 cycles we have -1. On the 2 cycles we have 2. Why? Because this representations is trivial on V4. And so V4 acts trivially on V0. So the characters of the 2 cycles will be 2. And then we have ij, kl, which is an odd cycle. So the character on these odd cycles will be like the characters of one of the transpositions. So 0 again. So this is the character table. Now we can use it. We can use this line to check that chi 5, it is irreducible. No? It was irreducible on S3, no? Acting on V0. So it remains irreducible when we act with S4 via this homomorphism. So row 5 here is the composition. Composed to pi. Right? But for instance, we can check that we can check some of the properties of this table. We can take, for instance, check that the chi 5 has norm 1 in the usual norm, or that I don't know. Okay, that we can check that. These two, for instance, are non-equivalent. You see that the characters are not identical as functions. These are one-dimensional. Cannot be equivalent to any of these because the dimension is different. But when you check the norm and the inner products between these characters, you really find that these characters are orthonormal in that norm. By the way, this was maybe here you see you have a homomorphism from S4 to S3. You remember in the lecture of Bus, there was also a homomorphism from S4 as the symmetries of F2 square projecting into S3 GL of F2 square. Or geometrically, this homomorphism, you can also see it like that. S4 acts on the cube in R3. And it permutes the long diagonal, no? The diagonal between opposite vertices. There are 4 of them. So when S4 acts permuting these big diagonals, and at the same time it induces a permutation of pairs of opposite faces. So that's the S3, the action of S3 in this geometric picture. So S4 permutes the long diagonals of the cube, and S3 permutes the pairs of opposite faces, which are 3 of them, no? Top and bottom, and 2 opposite faces on the side. Okay. So let's just check, for instance, that I have 20. I finish at 40, right? At 40? No, at 12, at 30. I finish at 11:30. So maybe instead of checking this, I go to another example. So we do now D5. Otherwise, I have no time. Okay. Now, I do a further example. So now we consider the group D5. So it's generated by R and S under the relation, 2 elements, R and S. R5 is equal to S4 is equal to the identity, and S time Rn is equal to R minus M S. You remember? So this group has 10 elements and has 4 conjugacy classes. 4, yes. So again, 4 irreducible, non-isomorphic representations. Non-isomorphic representation. And now we are going to compute the character table, actually we are going not only to compute the character table, actually to exhibit them, like we did for the other cases. So who are the conjugacy classes? Well, one is the identity, and then we have 2 conjugacy classes consisting of rotation and its inverse. So we have R and R minus 1, which is R4. And then we have, so this class has 2 elements, you see, cardinality of this class is 2. Then we have R square and R cube, yes, 2 elements. And then we have all the reflection. In this case, the reflection sits in the same conjugacy class. So we have all the reflections of the form R to the M. They are all in one conjugacy class, and they are 5. Cardinality of this class is 5. S, SR, SR square, and so on. So, okay, we have, as usual, the identity. Rho 1 is, the trivial representation, and with character 1, 1, 1, 1. Then we have another one-dimensional representation, which is distinct from this, and we see it from the character table. And this Rho 2 is defined like this. Rho 2 of R is equal to the identity, one-dimensional, this also. And Rho 2 of S is equal to minus 1. So we give it on the generators, and we can check that indeed all the relations of, this is really defines a homomorphism. So, for instance, we can check, I don't know, that Rho 2 of S square has to be equal to Rho 2 of 1, and indeed is, no, as 1, and no, 2 of S n is equal to rho S 1, and also minus 1, and this is, yeah, it is. Yeah, it's compatible. It's a homomorphism. So this is a one-dimensional representation, and then chi2, again, on the identity is 1. It is 1 on all these kind of rotations. 1, 1, and minus 1 on S. Okay, so these are two one-dimensional representations, and they are non-equivalent by theorem 3. No? Non-isomorphic. Now we need two more. And you remember, there is one way of viewing the n, the 5 in this case, is to see it via these matrices. So this, we call it like the birth certificate representation, is rho 3 means that rho 3 of R is equal to cos phi minus sin phi sum phi ros phi, where phi, you see, it has to respect the fact that R to the fifth is 1. So this phi is 2 pi over 5. Okay, so we take the, we have the pentagon, regular pentagon. So e to the I phi sits here. To the I phi. This is a primitive fifth root of 1. Okay. And then rho 3 of S is instead the reflection 1, 0, 0, minus 1. Also in this case, one can check that rho 3 is a well-defined homomorphism. So rho 3 is indeed a homomorphism from D5 to GIL. Okay, here we see R2, but if acts on R2, it acts also on C2. So it's a well-defined homomorphism. By assigning, with this, under this assignment on the generator, so we can check that it defines really a homomorphism. Okay. So now we have to compute the characters. So again, it's 1 on the identity. If we have a rotation, what's the trace of that matrix is 2 cos phi, right? 2 cos phi. And if we take the trace of R2 is 2 cosine of 2 phi. 2 phi. And then here, if we compose two matrices of this type, we get a reflection, and a reflection is always trace 0. No? A reflection, an orthogonal reflection in R2, if you think, has an eigenvalue equal to 1 and one equal to minus 1. No? The fixed line is 1, the one eigenspace, and the other is a minus 1 eigenspace. So we always get 0. And now we have chi4, and chi4, it is just a power of this in some sense. So R4, rho 4, I mean, four is, again, we assign it on the generator, and then we should check that it is indeed a well-defined homomorphism. R, instead of taking cosine of phi, we take cosine of 2 phi. Phi. And again, rho 4 of S is equal to the standard reflection. So again, rho 4 from D5 to GL2 C2, L of C2, it's a well-defined homomorphism. And we can compute the characters. Can you see if I write the last line here? Okay, so 1 on the identity. This time, the trace of the basic rotation is 2 times cosine of 2 phi. What? What? No, don't hear. Ah, 2, right, sorry. Of course, it is two-dimensional. Yeah, thank you. It's two-dimensional, right? The trace of identity is 2. The representations rho 3 and rho 4 are two-dimensional. So here we get 2 times cos of 2 phi, and here we get 2 times cos of 4 phi, and again, for the reflection, trace is always 0. Okay, now maybe if we, this phi is not a generic angle, it is a fifth of the round angle, so this psi 5 is related to cos phi in this way, so we have that psi 5 plus psi 5 bar, or equal psi 5 plus 5 to the minus 1 is equal to exactly 2 times cos phi. And if I do the cosine of 2 phi instead, 2 times the cosine of 2 phi, it is equal to psi 5 square plus psi 5 bar square, or psi 5 square plus 5 to the minus 2. For instance, if we want to check that each of these 2 lines have norm 1 in the norm of in this norm of the characters, we see that we will use some of these identities for primitive roots of 1. Look. So let's check, for instance, that chi3 has norm 1. So we have to do chi3 is equal to 1 over 10, and then 2 square plus 2 times, and now this square. So we have to do 4 times, or we have to do this. We have to square this. Psi 5. Psi 5 plus psi 5 minus 1 square plus 2 times, this time psi 5 square plus k5 minus 2 square. So what do we get? We get 1 over 10, 4 plus, and now we get 2 times. Now, psi 5 square, let's forget the 5 for a moment. 5 square plus psi minus 2 plus 2, no, double product, plus psi to the 4th plus psi to the minus 4 plus 2. Okay, now we have to use the relation psi to the 5 equal to 1. So what do we get here? We get 110. So 4 plus 2 times. So I get a 4. 4. And then I get psi to the minus 4 is psi. Is xi. Xi square is here. Plus I have xi cube is here. And then I have psi to the 4th. How much is this? Minus 1, right? This is minus 1. So, I get the sign. Plus. But I made a mistake somewhere. I have to get 1, right? No. What did I do wrong? Do you see? This is a plus? Okay. Attack. No. But one moment. Then I have a 4 also inside, right? Plus. Aiuto. So far. I had a 4 here, right? So I have a 4 here. Okay. So this is minus 1. So this is a minus 1, so I get maybe I should erase something. Anyway, I get 1 at the end. If I do the computation well, I get 1. So I have 110. I don't want to go over time, but far plus, I should get 1. Maybe try to figure, otherwise I'm late. Okay? Plus. So this is a minus 1. This is a, now I'm completely confused. This? This? Okay. So you get, I don't make it now. Let's just continue. I'm just going over time. It's not fair. Okay, we just do the computation later. Okay.